let us discuss this very important theorem. Okay, so this theorem says if you have any bounded sequence of R, then 100% it has convergent subsequence. Okay, so this thing we have to prove. So if you have any bounded sequence, it has a convergent subsequence. See what will I have done? I have taken one sequence. So let xn be a bounded sequence. Bounded sequence, that means which has upper bound, which has lower bound. The sequence will lie between these 2 points only. Getting? So this is a bounded sequence, I assume. And I am considering, let capital A be the range set of a sequence. So maybe you are thinking, what is range set? Let us see one example. If I consider a sequence xn is equal to minus 1 raised to n, then terms of that sequence will be, first one is minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 and so on. Getting the point? If I put n is equal to 1, 2, 3, 4 and so on, we will have all these terms. Then what will be the range set? Range set, that means distinct points. So in a range set there are only 2 points, 1 and minus 1. Actually 1 and minus 1 both terms are repeating infinitely many times, but there are only 2 terms in a sequence, okay, distinct points. So 1 and minus 1. So this is the range set of this sequence. But if you consider a sequence y is equal to 1 by n, then in that case terms will be 1, 1 by 2, 1 by 3, 1 by 4 and so on. So in that case range set will be 1, 1 by 2, 1 by 3. I should write the same set. I should write the same set because there is no any term repeating there. Okay. So this is a range set and this is also a range set. So there will be two possibilities. Either the range set is finite or the range set is infinite. Okay. So there are two possibilities for any sequence. So here also I am considering the first case, range set A is finite. If the range set is finite, but actually in sequence there are infinitely many terms, so we are generating infinite terms with the help of finite terms. That means at least one term in a sequence is repeating infinitely many times. As you can see here, 1 is repeating infinitely many times, as well as minus 1 is also repeating infinitely many times. But what I want to say, at least one term, okay, at least one term is repeating infinitely many times. So if you construct a subsequence of that term only, that means if you construct a sequence of these terms only, then we will have, so that means see I am generating a subsequence x and k is equal to 1, 1, 1, 1. I am just selecting second, fourth, sixth, eighth terms. Then obviously we will have a constant sequence, and we know that every constant sequence is convergent, so therefore we get a convergent subsequence. So in this way we proved, getting in this way we proved, yes, any given sequence has a convergent subsequence. Getting the point? So this is possible when set A is finite. Have you understood? I will repeat. See, if set A is finite, at least one term is repeating infinite times. So we will consider a subsequence of that term only. So we get a constant subsequence, but constant sequence is convergent. So that's why we get a convergent subsequence. So all such things I have written here. Okay, make a screenshot of it. After that, we will go for the second case. See, second case is A is infinite, range set is infinite. So infinite terms are there, just like this example, okay. So infinite terms are there. See, in that case, what we get, see, I have written A is infinite, but see, the important thing is sequence xn is bounded. Sequence xn is bounded, so that means what we get, so there is some lower bound and there is some upper bound. Getting? So all terms of sequence will lie in this interval only. So here also all terms of this set A will lie in between capital M and small m, bounded, lower bound and upper bound. So that's why capital A is infinite set which is bounded. Getting? A is bounded and infinite set. So we can apply Bolzano's-Weierstrass property. So Bolzano's-Weierstrass property say it has limit point. So therefore we can say A has a limit point. I am calling it as P. So you are familiar with the definition of limit point. Tell me what can we write. Let me remove this part. It is not required now. Okay. See, by definition of limit point, therefore, for every r greater than 0, BPR minus singleton P intersection A is not equal to phi, right? So for I'm choosing r is equal to 1. If I put r is equal to 1 here, BP1 minus singleton P intersection A is not equal to phi. So this intersection is not equal to phi, that means we can find one point from this set. Therefore, we can choose term xn1 of sequence xn such that what can we write, such that xn1 belongs to this ball BP1 minus singleton P. See, intersection A means term, A contains terms of sequence xn, getting now? So I am taking a term from A, that means this is a term of sequence xn. So therefore, we can choose term xn1 from a sequence which will lie in this ball, okay? For r is equal to 1 by 2. What will happen if I put r is equal to 1 by 2? B P 1 by 2 minus singleton P intersection A is not equal to phi. So again we can find some point from this intersection. Therefore, we can choose term xn2, okay, xn2 of sequence xn, I'm calling of sequence xn because A is a collection of terms of sequence xn. A is nothing but xn, you have to keep in your mind, okay? So I'm selecting a term from this set A, that means term of sequence xn. The condition is n2 should be greater than n1. Actually, I'm constructing a subsequence. No, so we should go further. We cannot come back. So our next term will n2 should be greater than n1, such that xn2 belongs to open ball with center P, radius 1 by 2 minus singleton P. So in general, what can we write? For r is equal to 1 by k. Tell me, if I put r is equal to 1 by k, what will you have? Therefore, BP 1 by k minus singleton P intersection A is not equal to phi. So again we can find some term. Therefore, we can choose x and k of sequence xn such that nk should be greater than nk minus 1, okay? Such that see, there is no more space to write. Make a screenshot of it and then we will go further. Such that x and k belongs to this open ball, okay, and so on and so on. So therefore, okay, therefore see, this point lies in a ball, so distance of that point x and k from center of ball is less than its radius 1 by k, okay? See, let me remove this part, it is not required now. See, but 1 by k tends to 0 as k tends to infinity. So therefore subsequence x and k converges to P, since distance between them is converges to 0. So that's why these points are moving together, they're coming together. So that's why this x and k converges to P as k tends to infinity. See, in this case we get a convergent subsequence. In previous case, that means where A is finite, in that case also we have proved it has a convergent subsequence. So in both cases we have proved the given sequence has bounded sequence as a convergent subsequence. So therefore we can declare every bounded sequence of real number has convergent subsequence. Simply I will mention hence the result. That means the entire statement is covered here, okay? So make a screenshot of it. After that we will stop. Thank you. Bye bye.